Next topic of concern is length contraction, and the way the textbook approaches this topic is to imagine like a traveler going from the sun to another star, and over time, here we have time on the y-axis and distance on the x-axis, the traveler goes from the sun to the star. Now, the way to approach this with a space-time diagram is to imagine, well, the traveler's time is going to be t sun over gamma. It's shorter. So from the traveler's perspective, the situation looks essentially like this, with the sun going this way, the star going this way. And here is, let's see, this is t traveler. This is going to be t traveler equals t sun over gamma. Now, the one thing that, I'm sorry, I have that on the screen. The one thing that, there's one thing that is common between these two things, though, is that the slope of this line, which is the velocity, the relative velocity between the traveler and the sun and the star, should be the same as this or equal and opposite rather, as the slopes of these lines. So we basically got the star over here covering this distance with the same velocity as we had before, and the t sun over gamma. So this distance we just call distance equals v times t sun, and this distance we say is distance v t sun over gamma. So the distance for the sun frame is v t sun. Distance for the traveler is v t sun over gamma. So d sun over d traveler equals v t sun divided by v t sun over gamma, which just makes this gamma. All right, so looking at that in a space-time diagram, here you can imagine, okay, let's say the green lines mark out the space in the sun's frame. So here's the sun, here's the star. Now we're going to change our velocity with respect to the sun and that star. And it goes like, what happens to the diagram is it looks like that. And then we look at the distance between here and here. The sun and the star are much closer together in this new reference frame. So that's what it would look like in the movable space-time diagram. All right, let's think about how we would do Lorenz contraction with the Lorenz transformations. And what we're going to do is we're going to start with two events, this event over here and this event over here. Actually, we don't need to do that. Let's use the one at 0 and delta x. 0 and delta x is the one we want to use. There's no time in our reference frame, there's no time between those events. So what we're going to do is take that pair of events and transform them so that they've moved. Okay, where did they move? Okay, where were they? Okay, so actually let me use I'll get one solid. So this dot here, this dot here where the dashed line meets the solid line, and I'm going to do the Lorenz transformation on that so that the dashed lines are horizontal and the solid lines are vertical. And now I'm going to look at where this event has moved. You'll notice that it has moved both in space and time, but the ratio we're actually interested in is the space versus space, the horizontal coordinate. So we're looking at things in our reference frame, and we want to know what it looks like in their reference frame. So going from our reference frame to their reference frame is a forward transformation. And so I'm going to use negative signs here. Negative sinh phi, negative sinh phi. Going from our reference frame, delta x is, I'm just going to say the length of the object is 1 in our reference frame, and the time between those two events is 0 in our reference frame. And this is actually going to give us two values. It's going to give us both the new position and time, but I'm only going to be concerned with the position. So we're going to take cosh phi times 1 minus sinh phi times 0, which comes out to be cosh phi. But you know what? I don't want a delta x. I want delta x prime. I don't want it to be 1. I want it to be delta x. I'm sorry. So cosh phi delta x. That gives us a nice ratio. On the other hand, with the delta ct prime, we get negative sinh phi delta x. So delta ct prime equals that, delta x prime equals this. And basically, we explicitly decided we're not interested in that desynchronization term. We're only interested in the ratio of length to length. So this is what we're getting, delta x prime over delta x equals cosh phi, which is also delta x prime over delta x equals cosh phi, which is cosh of arctanch v over c, or as more commonly referred to, it is 1 over square root of 1 minus v over c, quantity squared. But once again, we're only looking at this for the Lorenz contraction. So that means we're only looking at a comparison between where these lines intersect the x-axis here and where the same lines intersect the x-axis here. The other part, the hyperbolic sine part, had to do with a comparison between where this line, the dashed line, intersects where the vertical component of this dashed line here compared to the vertical component of this dashed line here.